In this video, we're going to take a bit of a look at trigonometry. So what we'll see is that rather than just being about triangles, like it may have been when you first learnt about it at school, trigonometry is actually more naturally expressed in terms of circles. So what I'm drawing here is what we call a unit circle. It's a circle that is centered at 0 and 0, and it has a radius of 1. So what I'm going to do is I'm going to choose myself a point on the circle, and I'm going to just mark that on here. Now from that point, what we can do is we can draw a line from the center of our circle, and if we then mark on the angle that goes between our positive x-axis through to that line we just drew anti-clockwise, then that's going to be the angle that we call theta that we're interested in. Okay, so now that I have drawn on my angle, I'd like to measure it using my protractor. So I'm going to line up 0 along the x-axis and count anti-clockwise, and I can see that my angle theta is about 110 degrees. So theta would be 110 degrees there. But alternatively, we can also go the other way around, clockwise, so long as we call the angle negative. So in this case, it would be negative 250 degrees, if I'm reading off clockwise. But in both cases, it's from that positive x-axis. Alright, so it turns out that the cosine of the angle theta, which we write as cos theta, it's literally just the x-coordinate of our point on the graph here. So that means that cosine of 110 degrees is just going to be what I can read off on my picture. So it looks pretty much like, in fact, we'll draw a line down to the axis so we can read it off more clearly. So that number is about negative 0.34, which is going to be our cosine of 110 degrees. Got 3 boxes plus a couple more squares. So it didn't require a calculator. I can just get an estimate of cosine 110 just like that. Now the same thing is, or a very similar thing happens for sine theta as well. So sine theta is just the y-coordinate of that point. So that means, again, we can just look at our graph and we can see that sine of 110 degrees, well, that's going to be about, going across to our axis, about 0.94 this time. So again, I didn't need a calculator. I could actually get a reasonable estimate of these values just by drawing them on my graph. So a related question is, what happens if we want to go the other way? So instead of having a point and an angle and trying to find sine and cosine of theta, so what happens if instead we want to know what theta is given a value of sine theta or cosine theta? So a question might be, if x is, for example, 0.6, what is the angle theta that makes cosine theta equal to 0.6? And another way we can say this is that the angle theta is the inverse cosine of 0.6. So what I can do is mark x equals 0.6 on my axes here, and then I'm going to draw a line and see what points on the circle have an x value of 0.6. Okay, you can see there are actually 2 points. There's one in the top half of the circle, and there's one in the bottom. And so I could draw some lines from the center of my circle to these points. And what that will give me is 2 possible angles to choose from. So inverse cosine of 0.6 doesn't just give me one possible angle, it seems to be giving me 2. So one of those angles is going to be positive because it's anti-clockwise from the x-axis, and the other one you can think of as the same angle but negative because it's going to be clockwise from the x-axis. We'll normally choose the one in the top half because that's what our calculator always gives us. If you use the inverse cosine button on your calculator, it's always going to give you that angle in the top half of the circle. So we're going to choose the top one as well. So what we can do is we can get our protractors and we can literally just measure the angle. So I'm remembering I'm going anti-clockwise from the x-axis, so that is going to be approximately, looks like 53 degrees. So cosine inverse of 0.6 will be about 53 degrees. We might check this on the calculator in a minute and see how close we got. So we can do a similar sort of thing for inverse sine. So this time where the question is if we have a certain y value, for example negative 0.9, then what angle is going to give sine theta equals negative 0.9? So what is our angle theta? So we'll once again mark our y value of negative 0.9 on our axes, and we'll just go across and find the points on our circle that have a y value of negative 0.9. We can see that once again there are two of them, and this time they both occur in the bottom half of the circle. That's because our value, negative 0.9, was a negative number. So we're once again going to have two choices of angle. And this time, no matter what that value is, we're always going to have one choice in the left half of the circle and one choice in the right half of the circle. Once again, there is kind of a preferred choice, so we'll generally tend to choose the answer that is in the right half of the circle for inverse sine, because once again, that's what your calculator will always give you when you use the inverse sine function. It'll always give you a number between negative 90 degrees, that's downwards, and positive 90 degrees, that's straight up. It will never give you a number in the left half of the circle. So the inverse sine of negative 0.9, we can get it by measuring that angle, once again, with our protractor. So again, I'll line it up so that 0 is along the positive x-axis, and I'm going to go clockwise this time, so it will be a negative angle, and it looks like it's around about between 60 and 70, maybe negative 64.5 degrees or something like that. Okay, so we've now had a reasonable amount of success. We have, without using a calculator at all, managed to work out sines and cosines and also inverse sines and inverse cosines. So what we should do now is we should see what our calculator actually gives us and see how well we did. So I'm going to go into my calculator, and the first thing I need to make sure I do is to check that my calculator is in degrees mode. So on this Casio one, I need to go Shift Setup to get in there and make sure that angle is set to degrees. Okay, so let's start with the inverse cosine. Let's go inverse cosine of 0.6, and sure enough, we get 53.13 approximately degrees. And that just lines up with what we got, so we're on a roll so far. Let's see how we did with the inverse sine of negative 0.9. So shift sine gives me the inverse, negative 0.9, and this time I get negative 64.2 approximately degrees. Okay, so we were out at a decimal place, but I don't think we need to worry too much about that. So from the calculator, we get negative 64.2 approximately degrees. Right, so I might let you figure out or test or check what we did earlier with the cosine and sine yourself in your own time. So you just go into your calculator, again make sure it's in degrees mode, and calculate the cosine and sine of those angles from the first part and see how well we did. The next question is, how do triangles come into this? So you've probably met this triangle before. It's got a right angle and an angle marked on. The long side of the triangle is called the hypotenuse. The side opposite the angle is called the opposite side, and the side that sits beside the angle is usually called the adjacent. So what we'll do is we'll flip our triangle around so that the angle is kind of lined up with the positive x-axis, like with our circle before. Now we're going to shrink the triangle down so that its hypotenuse is now 1. So this means dividing all sides of that triangle by h. Now, rescaling a triangle doesn't actually change any of the angles, that's just a property of similar triangles. So if we pop it into our diagram, you can see straight away that the x-coordinate, that's our cosine theta from before, will just be the adjacent over the hypotenuse. And the y-coordinate, that's our sine theta from before, that will just be the opposite over the hypotenuse. Okay, now you might be wondering, what about tangent? The tangent function is one more trig function that relates the other two sides of the triangle. That's the opposite and the adjacent. So in terms of our graph from before, basically we have that tan theta is y over x. It's the ratio of the y-coordinate to the x-coordinate. So if you like, it's the ratio of the height to the base of the triangle. It's also the slope of the hypotenuse, and that's why it's called a tangent, like a tangent line. So in terms of our triangle, this will become, therefore, tan theta is the opposite over the adjacent. So let's imagine that we have a triangle with opposite 2 and adjacent 5. So we know that tan theta will be 2 over 5, and so theta will be the inverse tangent of 2 over 5, calculated the same way as for sine and cosine, which will give us about 21.8 degrees. Okay. Imagine now that we take that triangle, we rotate it 180 degrees around, so that now the y-coordinate is -2 and the x is -5. Then our tan theta, using the y over x kind of definition, is now going to be -2 over -5, which will be 2 over 5, kind of just the same as before. So this brings up an important point, because that gives the same tan theta as our original triangle, even though the angle is now rotated around. So when you take inverse tan, say on a calculator, you'll always get a number between -90 and 90 degrees. So if you know that your number ought to be in the left-hand side of your picture, that means that the x-coordinate is negative, then you need to either add or subtract 180 degrees to get the right angle. Doesn't matter which, they're both the same thing. So for our second case, our angle would be 21.8 degrees plus that 180 degrees, which would give us 201.8 degrees. Or if you subtracted, you get 21.8 minus 180, you get negative 158.2 degrees in that case. Okay, so if you have a right angled triangle where you know two sides and you want to know the angles, or maybe you know one side and you want to know the other sides and the angle, one side and an angle and you want to know the other sides, then you can always use one of the three trig formulas to find the missing pieces. So for example, on this triangle, I have that the opposite is 2 and the hypotenuse is 3. So I can use the formula sine theta equals opposite over hypotenuse, which is going to be 2/3, to get theta is the inverse sine of 2/3 is 41.8 degrees. Or on this triangle here, I know that the opposite side is 4 and that this angle is 40 degrees. So the one that relates, if I want to find the adjacent, I can use the formula tan theta is opposite over adjacent, which rearranges to a times tan theta is the opposite, just multiplying both sides by a. And divide both sides by tan theta, so I'll get a is the opposite over tan theta. Plug it all in, 4 over 10, 40 degrees, and that gives me about 4.77 for my adjacent side. There are a couple of special triangles that we can get exact answers from. These correspond to the standard sort of sizes of set square that you might have had before. It's worth remembering these, or just remembering how to build these, because it saves you having to go for the calculator sometimes. So the first one, this is a triangle with angles 30 degrees, 60 degrees, and 90 degrees. And the sides of this triangle have length 1, 2 on the hypotenuse, and root 3. And then our second special triangle, that has angles of 45, 45, and 90, and it has sides of 1, 1, and root 2. So just using our formulae from before, we can read off what sine, cosine, and tan are for all of those angles. So that gives us sine 30 degrees is 1 over 2. That's just the opposite over hypotenuse for the 1, 2, root 3 triangle. Cosine 30 is root 3 over 2. Tan of 30 degrees is 1 over root 3. And you can continue on and fill out that whole table. Now, like I said, it's worth making a note of these triangles somewhere because they can just save you having to pull out the calculator. And you can always figure them out again if you can remember the dimensions of the triangles. Okay. Now, the last thing I want to talk about is vectors and components. So one immediate application of all this is resolving a vector like a force vector into components. So in 2D that would be like a horizontal and a vertical component. So in this course these will most commonly be force vectors, but it actually works with any vectors that you need. Right, so suppose I have a force vector F pictured like this one here, which has magnitude of 100 newtons. So I need to start by setting up my x and y directions. So make sure I do that so the positive y is anti-clockwise from positive x. And I'll draw them on like this. Okay, so the angle that I've been given is an angle, say, 20 degrees from the positive y-axis in the wrong direction. So before I can use my formulae from before, I need to make sure that I have the angle converted to being from the positive x-axis. So the angle I actually want is going to be 70 degrees. Okay, 70 plus 20 is 90. So my horizontal component, which I'll call fx, will just be my magnitude f times cosine of theta, it's the angle we just figured out. So that'll be 100 cosine of 70 degrees, which will be about 34.20 newtons. And my vertical component, well, that will be fy, which will be f times sine theta, which will be 100 times sine 70 degrees, which is about 93.97 newtons. So those numbers look about right. And if you follow this procedure, you'll always automatically get the right negative signs on things, even so if they're pointing in negative directions. So what I mean by that is if you always make sure your angle is counted from the positive x-axis, like we have all through this video, then you'll always get the right components by using the cosine and sine formula. What if we wanted to go the other way? Well, let's say we're given a force vector with components fx equals negative 30 newtons and fy is 50 newtons. We want to know the magnitude and the direction of this force vector. So we can calculate the magnitude using Pythagoras' theorem. So that will give us that the magnitude f will be the square root of fx squared plus fy squared. So that square root symbol, just also a little aside, that always corresponds to a positive number. And that's what your calculator gives you when you use the square root on it. So for us, that'll be f is the square root of negative 30 squared, careful to make sure the negative sign goes inside there, plus 50 squared, which will be the square root of 900 plus 2500, which is the square root of 3400, which is about 58.31 newtons. And we can calculate the direction in the same way that we did for our inverse tangent calculation before. So our vector is in the left-hand side of the plane. So you can recognize this by a negative x or a negative horizontal component. So we're going to need to add or subtract 180 degrees to get the right answer. So theta, that'll be inverse tan of fy over fx. Going to be plus 180 degrees because we know it's in the left-hand side of the plane, which will be inverse tan of 50 over negative 30 plus 180, which will be about negative 59.04 degrees plus that 180 will give us an angle of about 121.0 degrees. Now, if the horizontal component fx had been greater than or equal to 0, you'd just use theta equals tan inverse of fy over fx and not worry about that extra 180 degrees. Okay, so this video, we covered quite a lot. We started with the definitions of the trig functions cosine and sine, and saw how they very naturally just come from the x and y coordinates of points on a circle. We then connected these up to triangles, which is probably the context in which you'd come across trigonometry before. And we figured out that we can find all the information about the angles and sides of a right-angled triangle if we're given either two sides or one side and an angle, and you can use the formula to build the rest of it. And finally, we just talked about how we can take 2D vectors and resolve them into components using trigonometry. All right, so that'll do for now. We'll see you in the next one. Ka kite anō.